What's up, people? Welcome to my tutorial in anomaly detection. So in the previous videos we had a look at sampling data and the big overview of the algorithm that we're going to use. And in this video we're going to dive into the actual implementation. And before we do that, I want to mention some modifications that I did to the samplers here offline. So I'm calculating the mean and the max value here. We're going to see later how that looks in the code. Okay, cool. So let's dive into the implementation here. First of all, I'm just loading in the data from the sample that we did. And it's fairly undramatically. I'm not going to go into this thing, but it's from the config and the boundary here. You can see that for each variable, I now have a min and max value for this thing. I'm going to need that later to create a split point. Okay, cool. And then I create all the iForest. I find the anomalies, and then I calculate the accuracy of the algorithm. So let's go ahead and dig into the iForest here. And it's pretty straightforward. I go through the number of trees that we defined from the configuration, and then for each I do an iTree for this and push it into the forest. And we have this thing height limit here that is a variable we use for calculating if you hit the maximum depth, because we're going to create a binary search tree so it's going to have a point where you say that, okay, I'm not going to go deeper in the tree than this. And this is based on the subsampling size. So you're going to do math log on the sampling size because it's binary. You can use kind of like the inverse of exponential growth here to see that if we're growing exponentially from the bottom up, then it should be reasonable to have this kind of maximum depth, and that's what we use the log2 here for that thing. And then we just seal it so it's a whole integer. I got the number 8 for 256. And here is the interesting thing when we go to the iTree implementation. And as you know, it's the recursive algorithm. So yeah, first of all, we have the samples here. The current tree height is going to be initialized to 0, so it's recursive. So it's going to, for each depth that it goes, it's going to increment it. But it's going to start at 0. The height limit 8 as we calculated, and the boundary that we're going to need this data here to do stuff with. So first off, if the current tree height is greater than or equal to the height limit, then you hit the base case. Basically, we're never going to go deeper than 8 in this particular case. Or if you don't have any samples left, this is actually kind of nice. If you hit this thing here, then it means that you probably find some kind of anomaly, maybe. And they in the paper they call these external nodes, and what that means is that you are on a leaf somewhere in the tree, either in the bottom or before that if you don't have any samples left. We're gonna store the size because we need to have we need to know how many items there were left when we hit this thing. That's gonna be clear later. I've specified the attributes like this, hard-coded. There are other attributes here that we're going to use for other videos later in this series. But for now, these are the ones from the breast cancer CSV file that we're going to use. And here comes an interesting thing. From these attributes, you select a random one. So just a single attribute from this thing here. And that's going to be Q. So let's go ahead and skip to this thing here so we can see what happens. Okay, so Q in this, and this ran, it selected the mean radius. It could have been any one of these. And then what it's going to do is going to, for the Q mean radius here, it's going to find the min value and the max value and select a random point in between those values as the split point. And that's called P. So P here was 22.38 something for the mean radius, right? And here what it's going to do is going to take from the samples, it's going to filter out everything for the mean radius that is less than 22 dot something something. You go in the left, strictly less than this thing. You go in the left subtree, and everything that is greater than or equal to this value, you go in the right. So you're going to take this thing and say, okay, here's the split point. You go there and you go there, and then you're going to have a left and right subtree, and then you do this recursively for. Call the iTree for the left and the right subtree. You increment the depth here, +1 every time you do it, and then you pass along the height limit and the boundary. So it's gonna do this until it hits this base case here. And then we need to store what value and so the attribute Q we use for this split, and the split value was this thing here, and then the sampling size was 256 here. And then it's going to do that recursively until it's done with all the iterations. And then it's gonna put it into the subtrees, and then it's going to create a forest. And let's go ahead and skip here so we can see what happens. So now I have my forest, and these are the trees. So I've randomly created 100 trees here. So you can see here is a left, and then you can traverse this down. It's never going to go deeper than 8. It can be more shallow. So here was size 1 with an external node. Maybe this is an anomaly. Probably not, because it was pretty deep before it hit it, so it might not be that big of an anomaly. But here was a good one. It was just like one iteration, and then the right subtree was size 0, so maybe that's something. But it depends on what the other trees are going to have to say about it. So let's see how the anomaly is calculated. And here we get the data. This is the raw sample data, and then the forest that we created. This function here is just the helper function I created to calculate the average numbers of an array of numbers. So it's going to sum them up, and then it's going to do the sum over the items length. That's everything that it does. And then this thing here, it's grabbing one sample here, or it's going to iterate over all the samples that we have in the data set, and then for each sample is going to run through all the trees and calculate the path lengths for each tree. So you see here I have the forest of all the trees. I'm going to pass it x here, which is one specific sample, and then it's going to calculate the path lengths. So it's going to be, for each sample there's going to be 100 path lengths, and the path length is from the paper. So I suggest you pause the video and read through this path length here to see how it is implemented. But we're also going to debug it here. So if you hit an external node, this is the base case here. This is also a recursive algorithm, as you see. If you hit an external node, you return E, which is how deep it's going to traverse. So you see here you increment E for each iteration. So you start out at 0 at the root node, then you traverse for each depth in the tree +1, and the adjustment C thing is kind of involved, and I'll do my best to explain it in a good way. But let's say that you hit an external node, and the external node was terminated because you hit the max depth of 8. That meant that the size here, the tree size, is going to be greater than 0. Maybe it's 25 or something, so there was a lot of nodes left before you terminated. So if you just return this as the path length, that's not really a good way of saying how probabilistically long deep down in the tree it was, right? Because you did a very early termination, right? So what you do instead is you use this adjustment C function here to say that, I have this many items left. Probabilistically, it should have been, this long if it was evenly split or whatever, because it's a binary search tree. And this is equation 1, so it's going to be this thing here. So what you do here is you do, let's see, you do 2 times the harmonic number of n-1 minus this thing here, and the age function here is what they call the harmonic number, and it can be estimated by this thing here, the Euler's constant. So this is the harmonic number, this is the Euler constant. If n is equal to 1 or less, you're gonna have weird behavior. You don't want to do that. So that's gonna mean that you're doing a division by 0 here, and that's not a good thing. So if that happens, just return path length 0, because it means that yeah, you know, there were no items. So the harmonic number here and the rationale for this thing you can find. So that's the base case. And then it's gonna, you see the split value and the split attribute here. These are stored since before when we created the I-trees. So A here is going to be the attribute, is going to be mean radius because it's the first one, you know, that we looked at. And the split value is going to be 22 something, yeah. So this is the first thing. And then it's going to traverse it basically by that thing and until it hits the base case, and that's the path length of the thing. So take some time and let that sink in so you understand what's going on here. But I'm going to skip ahead a little bit and see what happens once we have calculated the path length here. So okay, at this point we had a sample, we ran it through all the I-trees that we created for one given sample. That's going to give us 100 estimations from the subtree saying, you know, this is kind of them voting of how long the path length should be. And then what you do is you calculate an anomaly score based on these things. So this is this thing here, score here. This is from the paper equation 2, if I'm not mistaken. Yeah, so it's this equation right here. And as you see here, E of h of x, this is the average of the hypothesis. So h of x here is the path length, basically. They're the hypothesis of how you know, deep it is. So you do an average on that, and that's why I created this get average thing here. So get average is the E function in the paper. And then you divide that by the adjustment C variable again for the sampling size of the whole data set, so 256 in this particular case. And then you do 2 to the power of that. And that's your score. So let's go ahead and look as you can see an actual score here. So it's going to be an integer, yeah, of an anomaly score. And then it's going to return that, and then it's going to, you know, concatenate that on the items array here, and then it's going to sort them descendingly just so that I have the top anomalies in the beginning of that array. That's everything that does, and then returns that scored items. A little bit heavy to process, I know that, but I would suggest that you debug it like this and then follow along in the paper to see that you understand what's going on here. And now I skipped ahead. So now we created all the anomalies here. We have the anomalies, and oh, it's quite big, so let's go ahead and look here instead. Yeah, we have the anomalies here. And yeah, 200, what is it, like 25,000 items here for each of the samples. And then it's going to take these and calculate accuracy here. And this is based on the accuracy that I calculate here is what is called the confusion matrix. So you'd have the true positives, false negatives, and true negatives. And I have a threshold that I use. Now it's set to 0.37 arbitrarily. But what I do is I do a min and max for all the attributes, or sorry, all the anomaly scores that we calculated to see what the boundary of the anomalies are. And if you watch my previous videos on data science, you would know how to do this thing. It's not particularly complicated. And then what you can do is you can calculate what's called area under the curve. So you would take the threshold and then you would run it once, calculate the score, step it up a little bit, calculate it again, step it again, step it again, step it again, and then you would do it between the min and the max scores. And then you can see you can plot the data, and then you can see what your precision and accuracy and sensitivity is, and then you can find a really good score. We're not going to do that in this video because that's going to be a little bit too much to go through, I think. I do some initializations here. The label that we're going to use is diagnosis. I have another data set that we're going to look at later, but I'm going to skip through this thing here. Minimax. And then here it's going to say, yeah, the number of negative and the number of positives. The reason why I do this thing here, it's because if you want to see how many actual negatives you have and how many actual positives you have, well, this is the first iteration, so it's not done yet, right? But it's we can have a look at that. And then it says that if your anomaly score was over the threshold that we set, and it actually was cancer in this case, then it was a true positive. If it was not actually true cancer, then it was a false positive. I thought it was a cancer, but it was not. Otherwise here, meaning that we were below the threshold, then, and it actually was cancer, then it was a false negative, and otherwise it was a true negative. And then what you can do, once you have calculated all of this thing here, let me go ahead and skip through the loop. Then what you can do is you can have the true positives, and then you can calculate the sensitivity of the algorithm like this. And you can calculate the specificity with the true negatives and the precision of the algorithm. And then I log this message. I think I'm just going to go ahead and skip it because it's more easy to read. But what I want to show here is also the number of negatives in this data set is very close to the number of positives in this data set. So it's what can I say? It's a data set that is called to be balanced. So you would have the same number of true positives as true negatives, and that's going to have some effects for this algorithm. So I'm going to go ahead and skip it. So the logs here, you can see that we had 25,000 samples. The minimum calculated score was 0.32. Actually, I'm going to run this in the terminal instead because it's hard to read with the colors. But it's the same data. And the mean score, the max score. So now I should be able to set a good threshold for this thing and play around with that a bit. True positives was about 7%. True negatives was about 36%. The false positives was 13%, and the false negatives was 41%. So I don't know. I wouldn't claim that this is a particularly good algorithm. Specifically, false negatives is not good, that you miss people who have cancer. If you say that they have cancer but they don't have cancer, it's not the end of the world. It's better. So you can get different trade-offs by playing around here with the threshold. Basically saying that if you want to be more conservative, what you classify as cancer, you can increase the threshold, run it again, and it's going to have other type of attributes. Now, with this being said, maybe you want to be more generous to say that people have cancer so you don't miss anyone. Then you lower the threshold, right? So you have no false positives, but I mean, everyone is going to, 50 is not going to be particularly good either, right? Because its sensitivity is way too high in this data set. So then you can, now that we run through the data set that we were using with the anomaly detection algorithm that this thing was, we can argue, okay, is this a good algorithm for this particular data set? And I would say that no, I don't think this is a good algorithm for this data set. And the reason why it's not a good why it's not a good algorithm, it's because the way the data looks. So remember, you have to figure out what is this algorithm doing, right? The algorithm, the way it works is have a data set, and then if you have outliers in that data set, that's what this thing founds. That's not at all how this is calculating the accuracy of the thing. Here we have a balanced data set where almost 50% have cancer and the other 50% does not. It's not going to be able to find any outliers in this data set. So with that being said, I think in this case, also it's not going to look for latent factors and stuff like this. So what you probably want to do in this case is run a different type of algorithm that can find, maybe you can do like an SVG or something to find latent factors, and then you can do classification on that, or just smack it into, I don't know, some graph and do Markov chains on that, or You can do a classical neural net that would probably work pretty well, depending on how much data you have. But my point is basically that you have to analyze your data, understanding how the algorithm works, understanding what type of data is needed for this algorithm to work, or if you want to see it the other way around. Because this thing here, I mean, independent of how you use the threshold for this thing, is never going to work particularly well, because what you're looking for are anomalies. And in the data set, when you have a 50-50 diagnosis labeled, those are not like anomalies, those are part of the data. Maybe it says something else, I don't know. But I hope it was somewhat clear what was going on here and that you weren't too confused about the things. Leave a comment in the comment section if you think that anything is like unclear, or like if you see any improvements on this thing. It's for me, I'm really struggling to try and be pedagogical with this thing, and feedback is welcome. And don't forget to subscribe also, of course, and otherwise I'll see you in the next video. Bye bye.